work that you're going to see presented by Leo today was largely performed during a 6-month visit to my research group here at WVU. As Leo will say in his introduction, he's at the University, I think you have the wrong screen here. He's at the University of Sao Paulo, and that's where he is currently resides. He'll be joining me as postdoc. I think this was mentioned yesterday, but he'll be joining me as postdoc starting in August if coronavirus is cured, but later if not, or there's a vaccine, very, very soon. So we're looking forward to seeing Leo, albeit perhaps a little bit delayed, but I hope you'll agree that it's a lot of work he managed to get done in 6 months. So I'll leave it to him to present.
Hi, so can you guys see the proper title screen now?
I can see it, yeah.
Okay, good. So hi, I'm Leo. Yeah, thanks for the introduction, Zach. So I'm last year PhD candidate here at the University of Sao Paulo, and hopefully I'll be joining WVU soon, back soon. And I'm going to talk a little bit about Illinois GRMHD. Please excuse me if I say IGM, but they are supposed to mean the same thing. I got used to saying IGM over time, and so nobody gets confused. I'm already setting the terminology right now. So the first thing that I want to say for those that are not familiar with IGM is that it is a rewrite, a 2015 rewrite of the original GRMHD code of the Illinois Numerical Relativity Group. It has been shown to have round-off error agreement with the original code, but it is twice as fast, and it contains a great reduction of the number of lines of code, and that's mostly due to removing dead code that was just lying around. It is completely open source and available as part of the Einstein Toolkit, as our fellow TCANers have already mentioned. It is capable of providing GRMHD support for dynamical spacetimes, and I mean the physics that it can analyze includes single neutron stars, binary neutron stars, with and without magnetic fields, black hole accretion disks, and many, many more. So what I'm going to be talking about today is where we still saw room for improvement in the code. So it was a code with good, but perhaps not great documentation. So that was one of the things that could be improved. It had hybrid EOS support, which I will also discuss a little bit in the next slides. And while most of the functions in there were ready for piecewise polytrope-based EOSs, not all of them were, and it was also lacking all the low-level infrastructure to handle those equations of state. And it has no neutrino physics or electron fraction available with that. So the talk that I'm going to be giving today will focus greatly on these three topics and our progress towards them. So the main goal when I arrived at WVU was to extend the equation of state support of IGM and add neutrino physics to it. But I wasn't familiar with the code back then. And so what I did was I learned how to navigate it, and to do it, in order to do it, I documented it. So it was not, although it had been designed to be user-friendly, it was not a great example of a literate programming in the new sense of the word. And so what I did was I documented it in pedagogical Jupyter notebooks alongside NeRP+, which I will also discuss a little bit more. So just so that you have an idea of what our documentation looks like, it would look like something like this, okay? So this notebook is already available at this link, which is essentially the NeRP+ repository. And you see that what we strive for is to have a tagged equation just before its implementation in the code. So our discussion is above, and you can see that the equations are implemented right here. And it's much easier to follow the discussion that way, because that way you can it's a lot better to, it's more human readable, let's say it that way. So going back to, so once I did this documentation, I started working on the hybrid EOS support of IgM. So it supports hybrid EOSs of this form, right, where the pressure was a function of the baryonic density, and that could be split into a cold part and a thermal part. And the thermal part is given essentially by a gamma law, equation of state. I think I can do this. Good. Can you guys see the pointer as well?
Yep.
Okay, so this gamma thermal index is basically, it tells us how efficient thermalization is at shocks. This is a constant throughout the simulation. And now the cold pressure, while it was already available in simple polytropic description, we have extended it for piecewise polytropic equations of state as well. So as a brief reminder for those who don't remember that, a simple polytrope is given by this relation between pressure and baryonic density, where K code and gamma code are constants that we use you start with one and you keep that throughout the simulation. While a piecewise polytrope, like our fellow TCANers mentioned in the previous slide, in the previous presentation, is more realistic and it's more physically based, and it consists of a series of simple polytropes. They are pieced together in a way that the pressure, the code pressure, is everywhere continuous. So you would have, so it's by construction, and you would have a relation like such as this one. However, the first derivative of the pressure is not. It's pretty clear from this plot here that it is not. And you expect to see some sharp features along the neutron star when you model it this way. But still, it's a much more realistic way of describing a neutron star than just a simple polytrope. So this implementation has been done and thoroughly documented using the Jupyter notebooks. So this is a picture of one of them. And in this notebook, if you run it from top to end, what you generate, for example, a mass versus radius plots for a bunch of known and well-known piecewise polytropic EOSs, and you can simply run this in your computer. It would take less than 5 minutes, I guess, to generate all these plots for you. And it's also well documented. There's also a bunch of other validations in there. It's already available at nerpplus.net, and for those interested, that's the name of the file that you need to look for. So we subjected our implementation to more stringent tests. So starting, for example, with a single TOV star, adopting a hybrid EOS where the code pressure is modeled by one of the piecewise polytropic EOSs in the previous plot, we have analyzed the drift on the central density as a function of time for two different resolutions. So we see that by doubling the resolution, the drift is much smaller, and you can ask how much smaller. Well, we multiplied the smaller one by 5, and we see a pretty good overlap, which indicates that the convergence order of the code is between 2 and 3, which is to be expected and in agreement with what other codes in the literature find, given that our shock capturing scheme is first order and our PPM reconstruction method is third order. So something between 1 and 3 is expected. After we have validated it for a single TOV star, then we ran a different test for a binary neutron star. So this is very similar to the plot, to the run that you've seen in the previous presentation. I think that the main difference is that the stars are more separated apart. I think they are at 50 kilometers instead of 32 kilometers apart. These are two equal mass neutron stars with 1.5 solar masses each, and we have not included the B fields in this run. So you see that after merger, we have the hypermassive neutron star oscillating up to the point where it collapses into a black hole. So these two were the main validations tests that we did to validate the piecewise polytropic implementation that we had. So once we reach that point, it's worth mentioning what is the current status of IGM inside the TCAN collaboration. And that is that the TCAN is planning to work with a handoff approach. So basically we have many phases during the in-spiral merger and post-merger. So basically the BMS in-spiral merger is going to be studied separately from the post-merger and black hole accretion disk phase. And the first part is going to be handled by IGM, while the second part is going to be handled by HARM, which I'm sure you will hear a lot more in the following two talks. And HARM, however, has already a head start when it comes to us, because HARM already supports tabulated equations of state. And it's also in a very advanced stage when implementing neutrino leakage schemes. And so because we want the two codes to communicate with each other, basically IGM will pause the simulation at some point, transfer the data to HARM, and then it will continue the simulation. Then our goal is to implement the same tabulated equation of state support and neutrino leakage infrastructure into IGM so that we ensure that we handle the data consistently between the two codes. And so the main motivation behind equations of state, of course, is that it is a much more realistic, it's the most realistic neutron star equation of state we have available as of now. We are particularly interested in the ones available at stellarcollapse.org. And so tune in tomorrow for Luke Roberts' talk, because I'm pretty sure it will be very interested and he will provide a lot more details on these equations of state. One of the complications that arise when we introduce these equations of state is that we now have new primitive variables, such as the temperature and the electron fraction, and that requires a massive update on the conservative primitive routines that we use inside the code, which are based on Dan Siegel's algorithms. So again, to keep the code consistent with HARM, we have been working with Scott and Ari, our fellow TCANers, to use their routines into our code. And we're also working with them on the neutrino leakage, which I will discuss soon. So tune in for their talks tomorrow. Sorry, it's today, it's not tomorrow. No, it's tomorrow. And here's what the current status with IGM. So our TOV solvers have been adapted and fully support tabulated EOS as of now. The code has been updated and all the functions that we need are in place and the code compiles. So stay tuned, because the work is ongoing and very soon we're going to have IGM working with tabulated EOS as well. So as of neutrino physics and leakage scheme, again, so in IGM, we have these complicated equations that were already implemented by hand in the original code. And now what we want to do is extend it in this form. So we want to introduce the electron fraction. This is a conserved version of it. Notice that it is YE star. So it's not the electron fraction itself. But now we have these new source terms at Q and R, which we are using HARM routine to compute. And they basically take into account variations of the electron fraction and momentum and energy due to the neutrino leakage. But implementing these things by hand, again, can be very complicated. And so to make our lives easier, what we opted to do was to use NeRPy. So I'm pretty sure that most people here are already familiar with it, but for those who are not, I will give a brief introduction to NeRPy now. So NeRPy is a Python-based code generation for numerical relativity and beyond. It's completely open source and available in the following link. And basically what it does is it takes Einstein notation tensorial expressions and convert it to highly optimized C code. So it's similar to Crank, but there's no Mathematica or Maple expensive license required. And it's completely open source and it's very permissively licensed. So just to give you a better idea, so it takes Einstein notation simple Python data structures such as lists, and it converts it to highly efficient C code with CSE, SIMD, and finite differences enabled. So CSE is common subexpression elimination. So for example, in this expression right here, we have sign of 2a appearing twice. And what the code does is it defines an auxiliary variable. Sorry, I can't reach that part of my slide. So it defines an auxiliary variable here so that the sign only has to be evaluated once. It also has the option to enable SIMD, which is single instruction, multiple data, so that the compiler can optimize the code in a way that we can compute sometimes multiple grid points in a single CPU cycle, greatly expediting the code and making it run a lot faster. So for example, just to give an illustration for those who are not familiar with it, to compute the second derivative of a simple scalar function phi, what we do is we write down this very human readable piece of code right here, where we basically set the spatial dimensions to 1, the finite difference orders to 2. This is not the derivative order, is just the truncation error order to which we're going to approximate the second derivative. We declare phi and an output grid function, which are just going to store the values that we want. We declare the second derivative as a rank 2 tensor with 2 down indices, which are what these big D's, this uppercase D's refer to, and the lowercase d indicate that it is a derivative. We can even impose that there's a symmetry in the first 2 indices of the tensor. And then we set, for example, the output to be the XX component of this tensor, and we ask it to output the code, and it will generate this mess, which is far more complicated to implement than this. But this one is error-free because the computer generated it for you. So once NeRPy has been debugged, which it has been a long time ago, this is completely reliable code, and it's much easier to implement it in this way than in this way. I hope everyone agrees with that. So what we strived to do then was to do a human-friendly version of the GRMHD source and flux terms. So with the help of Zach and Patrick Nelson, which is one of his PhD students, we have worked on the GRMHD source terms within NeRPy, and notice that the way that it is implemented, it allows for fantastic extensibility because you can input any gamma DD that you want. So as long as you derive or shift or alpha for that matter. So you can define this as symbols to match the variables in your code, and it would just generate the GRMHD equations for you. So it's a very powerful tool, and it makes our lives a lot easier. Not only that, but at the end of the day, you have highly optimized C code to work with. So this is the approach that we are using to implement the neutrino leakage scheme into IGM. So to give a summary of the results that we have obtained, we have the public IGM is already available with this link. Anyone can access it today. It is already documented and generated using pedagogical Jupyter notebooks. So you have a collection of notebooks that document the different aspects of the code. If you run all of them, in the end, you have a source directory with IGM ready to go. It already contains the latest piecewise polytropic and hybrid EOS support, and it has been validated through the TOV. That's a single TOV star test that we've shown, plus the full BNS merger. And as of ongoing work, which everyone should stay tuned because it should be ready soon, we have the highly optimized C code generation that we have implemented with NeRPy for the GRMHD flux and source terms. The tabulated EOS support is under development. Again, as I said, we already have implemented everything is in place. The code already compiled, so we're really, really close. And the neutrino leakage scheme is also under development, and I'm sure that Scott and Ari will discuss them in a lot more detail in their talks. So yeah, thank you.
Thank you very much. If you have questions, please raise your hand in the chat. And so Bruno, can you start your question?
Okay, I have a curiosity. The leakage scheme will be implemented as part of Illinois GRMHD, or is a sort of separate thorn that could also be coupled with other evolution codes, like, for example, Zelmani leakage?
So it will be part of IGM, but in the parameter file, you can specify whether or not you want to activate it. But it will be in the same thorn.
Yeah, my question was essentially if you will be able to use that leakage scheme with another evolution code, like, for example, GRHydro, or if instead it depends completely on IGM.
Yeah, currently it depends completely on IGM.
Okay.
Yeah, that's a current approach. There may be a couple subtleties there if you choose different conservative variables to evolve. That might complicate things, but I guess so long as it's well defined what it assumes the densitized energy and momentum variables are, for example, then what it assumes, then it shouldn't be too difficult to couple to other codes if moved into a separate thorn. So I like the idea, actually. We'll definitely think about that moving forward.
Mm-hmm. The beauty of it, though, is that once it is, everything is in place, the NeRPE infrastructure to compute the source terms and flux terms that are related to the conserved electron fraction, they can be, you can change that to support any variable that you want. So in principle, you can maybe use that to a different code, but as of now, it's tailored to IGM.
Okay, I think we have another question. Are there any other questions?
Yes, thank you. I have a question. Actually, I have two questions, if I may ask. So the first one is, you mentioned, and you were talking quite a bit about splitting your evolution on early evolution and long post-merger evolution. I'm afraid I didn't exactly get the point. Why would you want to split, even if you have to pass parts of one code into another code? So this is one first question. And the second one, you mentioned that you want to implement the leakage scheme into the evolution code. Are you only planning to implement the leakage or also momentum schemes like M1 or M0?
So regarding the first question, it is because the codes are better suited for those particular phases. So IGM is really good at the in-spiral phase, but the post-merger phase, specifically the black hole accretion disk, especially HARM, is just designed for that. And so it is just much better to just handle that part with HARM. But because IGM is better suited for the in-spiral, then it's just easier to do it with IGM. Regarding your second question, I'm not really sure.
Yeah, so IGM is a dynamical space-time GRMHD code. So if you have rapidly changing gravitational fields, like you do in the case of a in-spiraling binary neutron star and even hypermassive neutron star remnant, you've got to use a dynamical space-time solver to be self-consistent. So that's why we use IGM for that. But in terms of a long-term disk evolution, right? Imagine, so IGM uses Cartesian AMR for its gridding structure. Imagine the path that a fluid element needs to take in that disk along a Cartesian grid, right? It's a circular path on a rectangular grid. It's going to cross grid lines in exactly the ways we don't want through most of the orbit of a test particle in that disk. However, HARM implements spherical polar coordinates and was, as Leo rightly mentioned, completely designed for static space-time black hole accretion disks. So the idea is we let the black hole accretion disk settle down in IGM such that the space-time is more or less in a static phase, and then we hand off the data to HARM. And this will be, I'm sure, discussed in the next talk, in the next couple talks that you'll hear. the advantages. And I forget, what was your second question again?
Sorry, so the follow-up on the first one. So yes, I missed this point. So it means that the first code evolves it until the black hole formation, then there is a relaxation time, and then you pass it into the second code for the long-term evolution. Does it mean that you will not be able to evolve massive remnants where the space-time is still dynamic even when the remnant is formed?
So we've devised several measures of how stationary the space-time is, how static the space-time is. And obviously we'll be looking at those measures, and we will be exploring the extent to which we can continue performing these evolutions. I think, yeah, there are multiple unanswered questions regarding the handoff. We're just now seeing some success, so it's an exciting time. Certainly, I think for most disks, most binary neutron star mergers, the amount of matter in the disk is not so large as such that, assuming the space-time is more or less static and that disk is effectively in a static space-time environment, compare that to the other errors in a typical binary neutron star simulation, I would be surprised if it holds a candle to that. There are so many unknowns, but I think it's an important step forward. We certainly have a new spherical polar coordinate dynamical space-time code that the TCAN collaboration has been involved in releasing, and that is the first author on that was Vasily Mevis. And so handing off to a dynamical space-time code, that's definitely a possibility that we'll explore in the future as well. So I hope that helps to address your question. First question.
Yes, yes, thank you very much.
Okay, we have another question.
Hi, that's Agnieszka, and I just want to add from my comment that I also worked on this harm and the tabulated equation of state. I don't have a leakage scheme. Unfortunately, this is much simpler than neutrino treatment in my code. But well, I have this Fermi equation of state, and I will present this in more detail on my talk on Friday. So if you are interested, I will speak about this.
Okay, thank you.
You need that talk as well.
Are there any other questions?
Sorry, I can't find my hand off to raise my hand. Can I ask a question?
Sure.
Okay, so my question is for the NeRP future developments. So far, NeRP Plus is working in outputting C code. Any planning going into C++ in the future?
Well, I think that all the C code that NeRP outputs is fully compilable with the C++ compiler. So I don't see any issues at all using NeRP with the C++ as is. I think, right, so C++ obviously has a native object-oriented features and a lot of very cool features surrounding that. Yeah, I think NeRP is perfectly suited for C++ as is. I think the key advantage of using NeRP is the fact that effectively when you're typing in NeRP language, which is in Python, it's metaprogramming. So it is maximally flexible. And that's, I think, something that Leo illustrated quite nicely. You can use it with any code you like. Obviously, if you have a C or C++ compiler, that would be most useful because it outputs highly optimized C code. But indeed, yeah, I think I'm not aware of any incompatibility that you might experience with using it with a C++ compiler. And in fact, I think that Phil Chang is using it within his C++ wider infrastructure. Just as an example of a use case where you can. So great question.
Okay, we still have time for another question. Is there any other question that people want to ask? So we still want to keep the time. So even if there's no other questions, we're going to just wait a little under a minute for the next talk. So I'll just mention that the next speaker